Okay, so today then we're going to have a look at the estimation of dissolved oxygen in a water sample by redox titration. This is called the Winkler method. It is higher level only. There's a couple of things I have to do before I start my titration. Firstly, you're going to go to your river, your stream, whatever water sample is close by, and you rinse out the sample bottle with that water sample. Why? To remove any impurities and to avoid trapped air bubbles. You're then going to submerge the bottle completely in water to be analysed. Again, it's very important to submerge completely because we want to keep out as much air or oxygen as we can. So that's why we have to submerge it completely. And it's very important as well we fill the bottle to the brim because it prevents air being trapped under the lid. Some of this air contains oxygen. Some of that oxygen may be able to seep into our water supply, giving us an inaccurate result. So those are three things that need to be done before you even start your titration. You're then going to just place your stopper back onto your sample water. And using a pasteur pipette. And a pasteur pipette is the same as the graduated droppers that we have in school. So either or there is perfect. And you add 1 centimetres cubed of concentrated manganese sulfate solution, MnSO4. You need to know the name of that as well, manganese, under the water surface. And then 1 centimetres cubed of alkaline potassium iodide solution. Again, you need to know that, alkaline potassium iodide. I'm just going to bring your attention here to the word concentrated, and all these reagents are as concentrated as possible. And the reason for that is because we want them to sink to the bottom in order to react with all the oxygen that's present. The next thing I just would like to bring your attention to again is under the water surface. This is important because if I had my pipette or my graduated dropper above my water sample, again, it can pick up some air and oxygen on its way. So all of these are added under the water surface. Once we add in this concentrated manganese sulfate and the alkaline potassium iodide, we note the formation of a brown precipitate. You don't need to know the formulas there. Very important to note here that if the white precipitate remains, you could often be asked, what does that mean? It means there's no dissolved oxygen present. If I see that, I have to dilute. So I have to go back and I have to take half of my sample of my water sample, and I need to add in a half into the bottle of well oxygenated distilled water. And remember, in your calculation, you'd have to take that dilution factor into account. I will be looking at a calculation with you at a later stage. You're then going to shake vigorously for 30 seconds. That's to make sure that all of my oxygen has reacted. I then allow a brown precipitate that has formed to settle, and I see about 5 centimetres cubed of clear liquid at the top. Once that happens, then I'm going to add in, and again, you have to have the word concentrated, and this time it's sulfuric acid. Again, always added under the level of the water. We restopper, and again, we shake. And what we notice is that my brown precipitate has redissolved and my solution has turned a red-brown colour. That's because iodine is present. We're then going to titrate my water sample. So that's 100 centimetres cubed into a conical flask, and it's titrated against sodium thiosulfate. And we looked at sodium thiosulfate already, okay, where you have your red-brown colour. You then add in your sodium thiosulfate until that red-brown colour in my conical flask changes into a pale straw colour, okay? Then you're going to add in a few drops of starch solution as indicator. We note the blue-black colour and we continue until the solution is colourless. You then carry out 2 titrations that agree to within 0.1 centimetres cubed, and I will look at a sample calculation with you then.